Electrical circuit elements are described mathematically by the relationship between voltage and current at their terminals. The voltage-current relationship for resistors is called Ohm's law, which is the subject of this video. This is the circuit symbol for a resistor. R is the resistance of the resistor. The units of resistance are ohms, represented by the Greek letter omega. Now let's define a voltage difference between the terminals, V of t, and a current through the resistor, I of t. Notice that we've defined voltage and current to be consistent with the passive sign convention. Current is entering the positive voltage terminal. The relationship between voltage and current for a resistor is called Ohm's law. Ohm's law states that the voltage across a resistor is equal to the product of the current through the resistor and the resistance. So V is equal to I times R. This relationship can be rearranged in a couple of common ways. If we divide both sides by the resistance, R, we get V of t over R is equal to the current, I of t. And if we divide both sides by I of t, we find that R is the ratio of V of t to I of t. We'll use this circuit to investigate how to apply Ohm's law in a circuit analysis. We have a 5-volt source connected to a 2.2 kilo ohm resistor. We want to calculate what the current in this direction will be through the resistor. First, we need to define a voltage across the resistor according to the passive sign convention. If this is our positive current direction, that means this is our positive voltage terminal. This voltage, since this 5-volt source is applied here, is just 5 volts. Now applying Ohm's law to the resistor, we get I is the voltage, 5 volts over 2.2 kilo ohms, which is about 2.27 milliamps. Now let's construct this circuit, measure the current, and compare the measurement to our expectations. Using the analog discovery to provide 5 volts across this resistor, the DMM is measuring the current through the resistor. If I turn on power, I get the 2.27 milliamps that I expect. The relationship between voltage and current for a resistor can also be represented in graphical form. A graph of voltage as a function of current, or current as a function of voltage for a circuit element, is usually called the IV curve for the element. Mathematically, the voltage-current relationship for a resistor is voltage is equal to resistance times current. So for a resistor, the plot of voltage as a function of current is just a straight line that passes through the origin and has a slope that's equal to the resistance. Notice that when we measured the voltage and the current for our resistor in the previous demo, we were just measuring one point on this curve. So if we apply a voltage V1 and measure a current I1, we're getting a point on this curve, and the resistance is just V1 over I1. Alternately, if we're given this curve and we know, for example, how much current we want, we can read the necessary voltage directly from this graph. This desired voltage-current relationship is sometimes called the operating point. One advantage of IV curves over a mathematical voltage-current relationship is that they can be measured directly. So a common approach to determining the voltage-current relationship for a circuit element is to measure the IV curve experimentally and then determine a mathematical relationship that best describes the measured curve. Next, we'll look at this process in the context of resistors. When we applied a single value of voltage and measured the corresponding current, we got an estimate for resistance. However, any experimental data is prone to errors, so it's probably better to apply several different voltage levels to the resistor, measure their corresponding currents, and then calculate the resistance for each voltage-current combination. Then we can, for example, identify bad data points and disregard them, or average the calculated resistances and feel secure that a little error in any one measurement isn't completely skewing our results. Another and possibly better approach is to plot the various combinations of voltage and current against one another. Then we can draw a line that we think best fits the data. The slope of that line will give us the resistance. Individually measuring a large number of voltage and current combinations is pretty tedious. Luckily, there's a way to more or less automate plotting these characteristics. To do this, though, we need to apply a time-varying voltage to our circuit. If we apply a triangular voltage wave like the one shown here, the resulting current will also be a triangular waveform. Each point on the current curve will correspond to the voltage at the same time divided by the resistance. If we measure a bunch of different combinations of voltages and currents and plot the voltage points against the current points, that's our voltage current characteristic curve. A function generator can apply time-varying power, and our oscilloscope can measure time-varying voltages. But what about the time-varying current? Well, if we have a resistor with a known resistance, we can calculate a current through the resistor from a measurement of the resistor's voltage and the resistance value. This circuit allows us to measure an IV curve for an unknown resistor R. This is a known 100 ohm resistor. It's in series with the resistor we want to characterize. The current through the two is the same, since any current going through this resistor also has to go through this resistor. If the voltage across the known resistor is V1, then we can calculate the current as V1 over 100. We can then plot the voltage V2 against this calculated current. The slope of that line will be the unknown resistance R. This is the 100 ohm resistor. This is the unknown resistor. We're using the analog discovery to apply power and make our measurements. Channel 1 of the waveform generator is being used to apply power. Channel 1 of the oscilloscope is measuring the voltage across the 100 ohm resistor, and channel 2 of the oscilloscope is measuring the voltage across the unknown resistor. Now let's go over to waveform software. I'm using a triangular wave with a frequency of 100 Hertz and an amplitude of 5 volts. Switching to the scope instrument, the blue line is channel 1, the yellow line is channel 2 voltage, and this red line is a math channel. The math is channel 1 divided by 100, so this should indicate the current through both resistors. If I create an XY plot with current on the horizontal axis, the math channel number 1, and voltage across the unknown resistor on the vertical axis, we get a straight line. The slope of this line is the resistance of the unknown resistor. That gives us the theoretical background for resistors. In the next video, we'll talk about physical resistors. We'll talk about using digital multimeters to measure resistance, color codes on resistors to identify the resistance, and resistors with adjustable resistance.